We use this apparatus here to verify Joules law, and Joules law says that if you pass a current through a coil of wire here, well, the current squared is proportional to the increase in temperature in the water. And this is, of course, assuming that there are no heat losses to the surroundings, and we ensure this by having an insulated calorimeter here around the water. Okay, before we start, we just need to remind ourselves of another experimental result, and that is whenever you pass current through any wire or any coil, well, by experiment it can be shown that the heat produced is proportional to the current squared. Also, the heat produced is proportional to the resistance of the wire, and finally the heat produced can easily be shown to be always proportional to the time that the current is turned on for. Putting those three results together, we get the heat produced in a coil of wire under the current passing is the current squared by the resistance of the wire by the time the current is on for. And this is our starting point for Joules law. So up here we can say that the heat produced by the coil in this Joules law apparatus is I squared by resistance by time. And if we assume that all the heat produced by the coil goes into the water, i.e. there is no heat loss to the surroundings, well then the heat increase in the water is given by the standard equation, the mass by the specific heat capacity of the water by the change in temperature of the water, which we write as delta theta. And now we can rearrange this formula, because it turns out when we're doing the Joules law experiment, all of these quantities here are actually constant, R, T, M and C. R is constant because we're using the same coil all the time, it's the resistance of the coil. T is constant because what we're going to do is pass different currents through the coil for a fixed amount of time. So time will be kept constant for each current that we pass through. The mass is the mass of the water, that's constant, that never changes. And C is the specific heat capacity of the water. We keep the mass of the water constant by obviously making sure that we measure the same amount of water each time that we do the experiment, the exact same amount of water, before we pass the current through it. So the only two variables here are I squared and delta theta. And we can call those, as we usually do for graphs, we'll call, usually you call the thing that you're changing, you call that your x value, and the thing that changes as a result is the y value. There's x and there's y. And now we keep in mind our standard formula for the equation of a line in maths. We can rewrite this equation in a more familiar format as y equals mx plus c by dividing across by mc. So we get I squared RT over mc is equal to delta theta. Or I do it the other way around, delta theta is equal to I squared, let me just rewrite that slightly again, is equal to RT over MC times I squared. And now it's in the more familiar mathematical format, which is y equals mx plus c. And of course this in the blue circle here, that's all a constant. It's constant because the four quantities in that are all constant. So that would be the slope of our graph, RT over MC. By the way, don't get these two m's mixed up. This m is for, the blue m is slope, the black m is mass. So what this means is if we draw a graph of delta theta, well, that would correspond to our y-axis, and x would correspond, or I squared would correspond to our x-axis. And the slope of our graph would then be RT over MC. The plus C C is always where it cuts the y-axis, so that means it's plus 0, which means it goes straight through the origin. That's what the 0 means there. So if we look at the graph, and if we draw the graph, we should get a straight line like this, and again the slope m of our graph is equal to just to go back, it was RT over MC. I'm using color coding here. The blue M is the slope, black M is mass, just not to get mixed up here, so be careful with that. And so for example, in an exam question, if you were asked to work out the mass from the slope, well, all you'd have to do is you just rearrange this formula and fill in all the other values. You work out your slope from the graph, M, work out R, you'd have R, T, time will be kept constant for the whole experiment, and C, the specific heat capacity of water is also a constant. So you can work out your mass from the slope then. So just to go back to how you actually get the graph, of course, that's what the readings for this experiment are. You would take several readings of current squared and several readings of the corresponding delta theta, or change in temperature, and you get those, of course. You get your readings of current from the ammeter, and you get your readings of theta from the thermometer here. And so you take 5 or 6 readings, and each reading, of course, of I squared versus delta theta corresponds to a point on the graph, and you get points maybe something like this, and then you draw the line of best fit that goes through all those points. And finally, as I said, you work out the slope of this line by picking pick 2 points on the graph. Pick a point maybe there and pick a point there, and call them x1, y1 and x2, y2. Call that one x2, y2 maybe. And call the bottom one x1, y1. And of course, the slope, which I code as blue m, is y2 minus y1 over x2 minus x1. And then you get that value, fill into the formula, and that allows you to get any value you want here that might be missing. For example, if the mass was missing, you fill in your value of m here, and you get mass.